All right, well, I'm gonna make another video talking about the game of frictionless catch problem, the one that in the first chapter 4 homework assignment, I eventually said, you know what, let's just do this one later because it seemed so complicated and so involved that it was really aiming at stuff that we would get to by the end of the chapter. Also, I think it was kind of confusing because of how many variables there are and how many in the complications of the situation. So I'm going to go through the whole thing, and I think that when we're done, it's not going to be that bad. So first, we've got this situation of Chuck and Jackie on carts. The carts can slide without friction. You've got an inertia of Chuck and the cart. You've got an identical inertia for Jackie and her cart. They're initially at rest. Chuck picks up a ball and throws it. Jackie catches it. So because Chuck throws the ball, Chuck is going to get moved backwards. Because Jackie catches the ball, Jackie's going to get moved backwards from her point of view. And we're going to figure out some stuff about it. So the first question is to find the relative speed between Chuck and the ball. But first, before I do that, I'm going to draw out this situation just to be a little bit clear about what's going on. So we've got, first we have, at the beginning, we have Chuck. And we have Jackie over here. And they're both sitting on carts that are frictionless. I'm not going to draw the carts, but they're there. So Chuck has an inertia of m cart. Jackie has the same inertia of m cart. And their initial velocities are 0. Nobody's moving. V equals 0, V equals 0. And then there's also a baseball right there, which has an inertia of mb. And it's also not moving to begin with. And then Chuck throws the baseball. So Chuck throws the baseball. Baseball's here, and it's flying through the air. And because the ball went forward, its momentum changed. That means Chuck has to go backwards. His momentum changes too, an equal and opposite amount. So we've got a velocity for Chuck that's going backwards. We've got a velocity for the ball that's going forward. And we still have Jackie over here not moving. V equals 0. So we're going to figure out some stuff about that. And then finally, we've got Chuck still moving backwards. And we've got Jackie having caught the ball. And they both move backwards at whatever velocity of Jackie is. So that's 3 situations. We've got Chuck holding the ball, nobody's moving. We've got Chuck starting to slide backwards because Chuck threw the ball and the ball's going forward and Jackie's not moving. And then we've got Chuck sliding backwards and Jackie holding the ball and Jackie sliding backwards this way. So the very first question is about the relative velocity of Chuck and the ball. Let's look at what it says. It says, find the relative speed between Chuck and the ball after Chuck has thrown the ball. What does that even mean? So the relative speed of Chuck and the ball is basically how fast would Chuck say the ball is going? Well, since Chuck is, according to an observer who's sitting on the ground, saying, okay, well, Chuck is going backwards at v sub c, and the ball is going forward at v sub b, then they're getting farther and farther apart at a rate of the sum of those two things. So all of this picture is from the point of view of somebody who's sitting still on the ground. From the point of view of Chuck, things are a little bit different. From Chuck's point of view, Chuck is never moving, but the ball is moving faster than the person on the ground says. So the person on the ground, Chuck would say that the ball is moving VB plus VC. This is the most important part of the problem in order to set up all the rest of it. According to Chuck, the ball is moving faster than according to the ground. So let me go back over to the page and put that in. So I put u is equal to v sub b plus v sub c, and submit, and you can see, yep, that's correct, and it gives us some thoughts about what that means. What does the term relative speed mean? We're going to talk about that a lot more in the next few chapters. Okay, next, what's the speed of the ball relative to the ground while it's in the air? Interesting. So we're going to have to figure out what's going to happen in this interaction that caused Chuck to slide backwards and the ball to go flying through the air. But we're going to have to express it in terms of u. All right. So we're trying to figure out how fast the ball is going. So let's first do this in terms of from the ground's point of view, the normal one. What can we say about v sub c and v sub b? Well, we know that because the two momentums are equal and opposite, that means, so delta p for Chuck equals delta p for the ball, but negative, with equal and opposite signs. That means that the mass of the cart times the velocity of Chuck equals the mass of the ball times the velocity of the ball, right? Okay, now if I was really talking about velocities, because velocity has a sign in it, I should have a negative sign right there. But this question is asking about speeds. This is probably something that tripped up a bunch of people. The question is asking about speeds, so I can ignore that sign. So this is saying the mass of the cart times the speed of Chuck and the cart together equals the mass of the ball times the speed of the ball. That makes sense because the momentums, the magnitudes of the momentums have to be equal to each other. All right, so the question is going to be asking me, what's the velocity of the ball? Okay, well, rearranging that equation, I get the velocity of the ball equals the inertia of the cart divided by the inertia of the ball times the velocity of the cart. But then let me switch back to the webpage for a second. I want the velocity, the speed of the ball relative to the ground. So I'm not allowed to use v sub c in there. I need to use u. This is basically saying, well, let me change v sub c using this thing up here for what u is. Okay, so u is vb plus v sub c. That means vc equals u minus vb. So I'm going to substitute that in right there. So that means that the velocity of the ball is the mass of the cart divided by the mass of the ball, or the inertias, times u minus vb. Move that over a little bit so you can see it. Okay, I'm trying to solve for the velocity of the ball, but I see the velocity of the ball is on both sides of this equation. So I'm going to have to rearrange and simplify a little bit. So I've got velocity of the ball equals the mass of the cart over the mass of the ball times u minus the mass of the cart over the mass of the ball times v sub b. These two terms need to get combined, and that one needs to get left alone. So I'm going to move this over to this side. I'm going to say v sub b times 1 plus m cart over mass of ball equals mass of cart over mass of ball times u. This is getting complicated. And then I'm going to rearrange to solve for the velocity of the ball. So the velocity of the ball is m cart over mb times u over 1 plus m cart over mb. Almost there. How am I going to simplify that? I'm going to multiply the top and the bottom by the mass of the ball. That'll get rid of that fraction on the bottom, and I'll get velocity of the ball is equal to the mass of the cart over the mass of the ball plus the mass of the cart, all that times u. So I'm going to put that in for my answer. Go back to the web page and then write in fraction m sub cart divided by m sub b plus m sub cart times u, and submit. And uh-oh. Does it say m sub ball? Yep, so I found it. It actually says m ball, not m sub b. So I need to be careful about that when I'm writing out the stuff on the whiteboard. So then the next part, what is Chuck's speed relative to the ground after he throws the ball? Okay, so I'm trying to find out something about Chuck's speed relative to the ground. So I know the velocity of the ball relative to the ground. And I know Chuck's speed in terms of the velocity of the ball, right here. I know the velocity of the ball is equal to the mass of the cart over the mass of the ball times the velocity of Chuck. So basically, I want to combine these two equations to get an expression for the velocity of Chuck using u instead of v sub b. Okay, so I'm going to take that. So velocity of Chuck equals m ball over m cart times v b. And then I'm going to use this expression I just got for v sub b and put it in there so that I only have a u in there. So v sub c equals m ball divided by m cart times m cart over m ball plus m cart all times u. And then there I can see I've got m cart on the top and the bottom of that fraction. So that means I've got m ball over m ball plus m cart times u. So I go back over to here and say fraction m ball divided by m ball plus m cart times u, and submit it. There we go. All right, the last two parts are about Jackie's speed. What's Jackie's speed relative to the ground after she catches it? And then what's Jackie's speed what's Jackie's speed relative to the ground in terms of the velocity of the ball? Then what's Jackie's speed relative to the ground in terms of u? All right. So to do that, let's go back to the whiteboard again and look at the situation. So we're talking about this moment here when Jackie catches the ball. And we know at that moment that Jackie doesn't really need to know about what happened with Chuck at all. Chuck's no longer involved. It's just the ball and Jackie. And we have the mass of the ball times the velocity of the ball. That's the momentum coming in. Equals, well, afterwards, the ball and Jackie together are moving. So you've got the mass of the ball plus the mass of the cart, because it said that Jackie and Chuck have the same inertias when they're on top of the carts, times velocity of Jackie, because they're all stuck together. So the question just asks, what's the velocity of Jackie in terms of the velocity of the ball? Actually says that's v sub b. So then I need to divide this over to the other side and rearrange, and I get velocity of Jackie is the mass of the ball over the mass of the ball plus the mass of the cart times velocity of the ball. There we go. So then I can take that back over to here and write m ball divided by m ball plus m cart times v sub b. And submit. And I got it. All right, and then the last one, I want the Jackie speed relative to the ground in terms of u. Okay, well, I already figured out Jackie's speed in terms of v sub b relative to the ground. And I know from up here the relationship between u and v sub b. And I also know the expression I already worked out in one of the early parts for the velocity of the ball in terms of the velocity of the ground. That's actually the one I'm going to write down again. So this earlier result I got was that the velocity of the ball equals the mass of the cart over the mass of the ball plus the mass of the cart times u. So this is the velocity of Jackie in terms of the velocity of the ball. I want it to be in terms of u. So I'm going to substitute this in right there. So this goes there, and I'm going to get that the velocity of Jackie equals mass of the ball over the mass of the ball plus the mass of the cart times this thing, the mass of the cart over the mass of the ball plus the mass of the cart times u. And then I can simplify that a little bit by combining the two fractions. This is multiplied, so that's m ball times m cart over m ball plus m cart squared, all that times u. So that's the velocity of Jackie in terms of the u. So then I got to take that and put it back in the final results, and I'll get m ball times m carts divided by let me put it all into one fraction, m ball times m carts divided by m ball plus m cart squared times u, and submit, and I got it. So that's it. I think this is a little bit of a mess because of all of the variables and the subscripts and all of that, but conceptually it is really just, I know the word just is maybe a little unsatisfying, but it is just an interaction between Chuck and the ball flying through the air, and then figuring out something about the relative speed of those two objects. Then figuring out how fast those two things must be going in terms of each other and in terms of that velocity relative to each other. And then we've got another interaction between the ball and Jackie and figuring out her velocity in terms of the ground speed and the speed relative to Chuck. All right.